What happens to your old Duracell battery after it dies? Does it disappear, or does it have a secret second life? Every year, millions of discarded Duracell batteries are salvaged, stripped down, and reborn, extracting valuable metals like zinc, manganese, and steel to power the technology of the future. Inside state-of-the-art recycling plants, a fascinating journey turns toxic waste into treasure. This is how over 450 million Duracell batteries are recycled each year in a factory. Before Duracell batteries can be replaced, they have to be made. It starts with zinc, manganese dioxide, and steel, materials chosen for their power and durability. At Duracell's factories, these ingredients are blended, shaped, and sealed with an electrolyte solution, creating the batteries that power everything from remote controls to flashlights. But once they run out of juice, their real journey begins. To keep millions of used batteries out of landfills, Duracell has made recycling easy. Drop-off bins at supermarkets, electronics stores, and recycling centers ensure old batteries don't go to waste. In France, a partnership with Corpile provides collection boxes for easy disposal. Businesses and auto shops also send in used batteries, making sure every last one gets a second life. Once collected, Duracell batteries are transported in specialized containers designed to prevent leaks, overheating, or short circuits. These containers are lined with non-conductive materials to reduce fire risks, while larger shipments, especially industrial or automotive batteries, require extra precautions. Trucks carrying them are equipped with temperature monitors and fire suppression systems, ensuring safe transport from collection points to recycling plants. Some companies even use drones to monitor collection bins in remote areas. These drones scan battery levels and signal for pickup when bins are full, preventing hazardous waste from sitting too long. In cities, smart recycling stations with weight sensors automatically notify plants when they're at capacity, making collection faster and more efficient. At the recycling facility, the first step is sorting. Different battery types require different recycling processes, so proper classification is key. Duracell's alkaline batteries follow a separate path from lithium-ion, nickel metal hydride, or lead-acid batteries. Mixing them up could cause chemical contamination, or worse, dangerous reactions. In smaller recycling facilities, sorting is still done by hand. Workers inspect each battery's label, shape, and weight to figure out what type it is. Since Duracell's alkaline batteries are among the most common, workers need to quickly separate them from other household batteries. It's an effective method, but it takes time. That's why larger recycling plants have turned to automation. At high-tech facilities, batteries move along high-speed conveyor belts, where AI-powered cameras and X-ray scanners analyze them in seconds. These advanced systems detect the battery's chemistry, size, and condition with incredible accuracy. Any that don't match their expected category are flagged for manual inspection. The most sophisticated plants even use robotic arms to pick out defective or mislabeled batteries, making the process even more precise. Larger batteries, like those from electric vehicles and industrial power cells, require extra care. They're too big for regular sorting lines, so robotic arms carefully dismantle them, breaking them down into smaller parts before sending them into the recycling stream. Whether done by hand or machine, the goal is the same, making sure every battery ends up in the right place for processing. This is where things get serious. Before the batteries can be shredded, they have to be made completely safe. Many still hold a small charge, and if not handled properly, they could spark fires, release toxic gases, or even explode. To prevent this, recycling plants use different methods to neutralize them before breaking down. One of the most effective techniques is freezing them in liquid nitrogen. This rapidly drops the temperature, draining any remaining energy and eliminating the risk of fire. Some facilities take a different approach, sealing batteries in chambers filled with inert gases like argon or nitrogen. With no oxygen in the air, combustion becomes impossible, especially crucial for lithium-based batteries, which are prone to overheating. Another method involves controlled electrical discharges, where machines send precise, low-voltage currents through the batteries to safely drain any leftover charge. It takes longer, but it also allows facilities to recover small amounts of reusable energy. Once the batteries are completely neutralized, they're finally ready to be shredded. Inside massive industrial shredders, razor-sharp steel blades rip through the batteries, grinding them into tiny fragments. These machines spin at incredible speeds, some at over 2,000 revolutions per minute, creating a deafening mix of clanging metal and snapping plastic. In just seconds, solid batteries are reduced to a chaotic pile of shredded steel, copper, aluminum, plastic, and the most valuable material of all, a fine dark powder called black mass. But shredding is just the first step. Now, everything has to be sorted. The shredded pieces move along conveyor belts, passing through a series of specialized extraction systems that separate each material. First up are the ferromagnetic metals. Powerful magnets pull out nickel, iron, and cobalt, which are key ingredients for making new batteries. To ensure purity, some plants use variable strength magnetic separators, which fine-tune their pull to grab only the desired metals while letting others pass through. Once collected, these metals are sent off for further processing, where they're melted, purified, and cast into fresh ingots, ready to be used again. For non-magnetic materials like aluminum and copper, a different approach is needed. Electromagnetic fields generate repelling forces that push these metals into separate collection bins, keeping them from mixing with other materials. The recovered aluminum is often used to make new battery casings, while copper, commonly found in battery wiring, gets repurposed for electrical systems. Lighter materials, like plastic casings and paper residues, are separated using high-speed air jets. Some advanced recycling plants take it even further, using fluidized bed separators that combine air and vibration to lift and sort materials with extreme precision. These steps ensure only the purest, most valuable elements continue through the process. But the real jackpot in battery recycling is black mass. This fine dark powder is packed with essential elements like lithium, manganese, and zinc, the key ingredients needed to make new batteries. Extracting these metals is where the real science happens. There are two means to recover metals from black mass: hydrometallurgy and pyrometallurgy. Hydrometallurgy is the preferred method because it's more precise and environmentally friendly. The process begins by submerging black mass in powerful acidic solutions, typically sulfuric or hydrochloric acid, which dissolves the metals into a liquid. This creates a metallic soup where each element can be separated. To isolate specific metals, specialized reagents are added to the solution. These chemicals act like magnets, binding to certain elements and pulling them apart layer by layer. Lithium is usually extracted first, appearing as a fine white powder called lithium carbonate. Cobalt follows, forming deep blue crystals that are refined for use in battery cathodes, aerospace technology, and even medical devices. Nickel comes last, settling into a pale green compound known as nickel sulfate, a critical material for stainless steel and energy storage. Pyrometallurgy takes a more intense approach, using extreme heat to break down shredded battery material. Inside massive electric arc furnaces reaching nearly 3,000 degrees Fahrenheit, metals naturally separate based on their density. Heavier elements like cobalt and nickel sink to the bottom and are collected in liquid form, while lighter ones, like lithium, rise to the surface and are skimmed off for further processing. Any leftover impurities are burned away, leaving behind high-purity metals ready to be reused. Once extracted, these metals go through a final cooling and solidification process. The molten materials cast into ingots, large metal blocks that can be easily transported and reprocessed. To prevent cracks or weak points, cooling chambers carefully regulate temperature changes. Some facilities use air cooling, where powerful fans blow cool air over the metal, while others use water cooling, submerging red-hot ingots in tanks, creating dramatic bursts of steam. A hybrid method, combining both techniques, ensures uniform cooling and maximum durability. The recycled metals recovered from Duracell batteries power the world in more ways than just one. Lithium is used to make new energy cells for smartphones, laptops, and electric vehicles. Nickel strengthens wind turbines and stainless steel, while cobalt plays a vital role in medical devices like pacemakers. Recycling these metals help cut down on destructive mining, which is not only costly, but also incredibly resource-intensive. Traditional lithium mining alone requires nearly 50,000 gallons of water per ton, a staggering amount that can be saved by giving old batteries a second life. Duracell's commitment to sustainability goes far beyond just recycling. The company has overhauled its packaging, swapping nearly all plastic blister packs for recyclable cardboard. Today, 85% of Duracell's packaging is made from recycled materials, cutting down on waste and reducing its environmental impact. The batteries themselves have also evolved. Duracell has eliminated heavy metals from its alkaline batteries, using safer alternatives like zinc and steel. On the production side, they're actively working to cut water and energy use while reducing CO2 emissions, aiming to lower waste by at least 21%. In Belgium, Duracell is making an even bigger shift, transitioning to 100% renewable energy, with solar panels now powering their factories. To get more people involved, Duracell has launched large-scale educational campaigns to encourage battery recycling. In 2020, they teamed up with the Reforest Action to plant 20,000 trees across France, Peru, and Tanzania, helping offset carbon emissions while promoting environmental restoration. By combining battery recycling with reforestation, Duracell is creating a more sustainable system where old batteries are transformed into raw materials for new ones. As battery demand continues to rise, recycling technology is evolving. Duracell and other industry leaders are investing in direct recycling, a method that recovers materials without the need for extreme heat or harsh chemicals, making the process even cleaner. Scientists are also exploring new battery chemistries that use more abundant, eco-friendly materials. In the near future, we could see a world where nearly 100% of battery components are recovered and reused, eliminating the need for destructive mining altogether. And that's how over 450 million Duracell batteries are recycled each year, turning discarded power cells into the materials that will power the future. What surprised you the most about this process? Let us know in the comments below. If you enjoyed this behind-the-scenes look, make sure to like, subscribe, and check out our next video on how aluminum cans are recycled into brand new products. What happens to your old phone battery after it dies? Does it disappear, or does it have a secret second life? Every year, millions of discarded batteries are salvaged, stripped down, and reborn, extracting rare metals like lithium, cobalt, and nickel to build the technology of the future. Inside state-of-the-art recycling plants, a fascinating journey turns toxic waste into treasure. This is how 160 million batteries are recycled each year in a factory. Before a battery can be replaced, it has to be collected, and that's more important than it sounds. Left in landfills, batteries can leak harmful chemicals like lead and lithium, polluting the environment. In Germany and Sweden, strict laws require people to drop off used batteries at supermarkets, electronics stores, and recycling centers. In North America, collection is most voluntary, with programs like Call to Recycle setting up drop-off locations, while companies like Tesla and Apple recycle old batteries directly. Once collected, the batteries are transported in specialized trucks to prevent leaks or overheating, ensuring they reach recycling facilities safely, where the real transformation begins. Not all batteries are the same, and that's why sorting is such a critical step. Each type, lithium-ion, nickel metal hydride, lead acid, and alkaline, needs a different recycling process. Mixing them up could cause serious problems, so accuracy is key. In smaller facilities, workers manually inspect batteries, checking labels, size, and shape to determine their composition. But in high-tech recycling plants, machines do the heavy lifting. Spectroscopy and X-ray scanners analyze each battery in seconds, identifying its metal content with pinpoint accuracy. Batteries travel down high-speed conveyor belts, where AI-powered cameras and sensors detect anything out of place. If a battery doesn't match the right category, it's instantly removed. This automation speeds up the process while ensuring precision. Electric vehicle batteries, which are much larger, require special handling. Robotic arms carefully dismantle them, breaking them down into smaller modules before recycling. This is where things get intense. Batteries aren't just metal and plastic. They're packed with stored energy, which makes breaking them down a tricky process. If a charged battery is shredded without the right precautions, it could catch fire, explode, or release toxic fumes. That's why safety comes first. To prevent accidents, high-risk batteries, especially lithium-ion ones, need pre-treatment before shredding. Some are frozen in liquid nitrogen to neutralize any remaining charge. Others are placed in sealed chambers filled with inert gases to eliminate any risk of combustion. Another method involves controlled electrical discharges, where small, precise currents drain out any leftover energy. Once these safety measures are complete, the real breakdown begins. Batteries are fed into massive industrial shredders equipped with razor-sharp steel blades. These machines tear through casings, grinding batteries into tiny pieces. Some shredders spin at over 2,000 revolutions per minute, creating an ear-splitting mix of clanging metal and snapping plastic. In just seconds, a solid battery is reduced to a chaotic mix of metal shavings, plastic bits, and a fine dark powder known as black mass, the most valuable part of the recycling process. At this point, the shredded material is a mess of different components: aluminum, steel, copper, plastic, and black mass, all mixed together. Separating these materials is the next big challenge, because improperly sorted elements can contaminate the final product, making it harder to reuse. The process starts with powerful magnets positioned along conveyor belts. These pull out ferromagnetic metals like nickel, iron, and cobalt, which are key ingredients in new battery production. Nickel and cobalt are especially valuable, but leftover steel from battery casings can interfere with the purity of the recovered metals. To fix this, some recycling plants use variable strength magnetic separators, which fine-tune their pole to extract only the desired metals while letting the others pass through. While magnets work well for iron-based metals, non-magnetic materials like aluminum and copper need a different approach. That's where eddy current separators come in. These machines generate electromagnetic fields that repel non-ferrous metals, pushing aluminum and copper into separate collection areas. This ensures that high-purity aluminum can be used in new battery casings, while copper, commonly found in battery wiring, can be repurposed for electrical applications. With the metals removed, what's left are the lighter materials, plastic casings, and paper residues. These are separated using high-speed air jets, which blow away lightweight debris. Some recycling facilities go even further, using fluidized bed separators that combine air and vibration to lift and separate materials with extreme precision. This level of detail ensures that only the purest, most valuable elements move forward. But the real prize in battery recycling is the black mass. This fine powdery substance is packed with lithium, cobalt, manganese, and nickel, the most sought-after metals in battery production. Extracting these materials requires specialized chemical processing, where advanced techniques break down black mass into reusable raw elements. Once collected, it's sent off to chemical processing facilities where the final transformation begins. Now comes the real science, the stage where valuable metals are extracted from the black mass and turned into reusable materials. The process needs to be precise, efficient, and environmentally responsible. Recycling plants use two main methods: hydrometallurgy and pyrometallurgy. Many facilities combine both to get the best results. Hydrometallurgy is the more common method because it allows for highly selective metal recovery. This process works by soaking the black mass in giant vats filled with acidic solutions like sulfuric or hydrochloric acid. These bubbling chemical baths dissolve the battery materials, breaking them down into their base elements. To separate them, special chemical reagents are added, binding to specific materials and isolating them one by one. Lithium is the first to be extracted, appearing as lithium carbonate, a fine white powder similar to sugar. It's then purified and sent off to be used in new battery production. Next is cobalt, one of the most valuable metals in the process. It crystallizes into a striking blue material, which can be refined further for use in battery cathodes, aerospace technology, or even medical devices. Nickel comes last, forming a pale green compound known as nickel sulfate, a key ingredient in batteries and stainless steel manufacturing. One of the biggest advantages of hydrometallurgy is its energy efficiency. Compared to high-temperature methods, it uses less power, produces fewer carbon emissions, and allows for the recovery of multiple metals at high purity levels. But some materials are too stubborn for acid baths and need a more intense approach. This is where pyrometallurgy comes in. Unlike hydrometallurgy, which dissolves metals in liquid, pyrometallurgy relies on extreme heat to melt and separate battery acids. The shredded black mass is fed into massive electric arc furnaces, where temperatures reach nearly 3,000 degrees Fahrenheit. As the materials melt, they naturally separate based on their density. Heavy metals like cobalt and nickel sink to the bottom and are collected in liquid form before being cast into solid ingots. Lighter elements, such as lithium and aluminum, rise to the surface, forming a layer called slag. This slag is then processed separately to extract lithium. To further refine the molten metal, flux agents, chemical compounds that attract impurities, are added. These impurities float to the top and are skimmed off before the metals cool. Once the metals are fully extracted, they move on to the final stage, Cooling and solidification, where they take shape before being sent back into manufacturing. Once purified, the molten metals must be carefully cooled and cast into solid ingots. Large rectangular blocks of raw material can be easily transported and processed. The cooling process is crucial because if the metal solidifies too quickly, it can develop structural cracks, making it unusable for high-performance applications. To avoid this, recycling plants use specialized cooling chambers that regulate temperature changes in a controlled manner. There are multiple cooling methods, each designed to produce high-quality metal ingots. Air cooling is one of the more common methods. Large industrial fans blow cool air over the molten metal, gradually lowering the temperature until it solidifies. This method prevents thermal shock, ensuring that the final product remains its strength and integrity. Water cooling is another widely used technique. Red-hot ingots are carefully submerged in water tanks, creating dramatic bursts of steam as the metal rapidly cools. This process speeds up solidification, but must be carefully managed to prevent internal defects. Some facilities use a combination of both, starting with air cooling before transitioning to a water bath. This hybrid method ensures a uniform cooling process, producing high-strength ingots that can be reintroduced into the supply chain. Once cooled, these shiny ingots, containing purified lithium, cobalt, nickel, and aluminum, are inspected for quality. Any imperfections are identified and corrected before the materials are shipped out for reuse. The recovered metals have countless applications. Lithium extracted from old batteries is used to manufacture new lithium-ion cells, powering everything from smartphones and laptops to electric vehicles and solar storage systems. Nickel is an essential component in wind turbines and stainless steel, while cobalt plays a crucial role in medical devices such as pacemakers. Beyond just resource recovery, battery recycling is helping to reduce dependence on environmentally destructive mining operations. Extracting 1 ton of lithium through traditional mining methods consumes nearly 500,000 gallons of water, a staggering amount that can be avoided through efficient recycling. As demand for batteries continues to grow, recycling technology is evolving at a rapid pace. With breakthroughs in direct recycling, more efficient chemical extraction methods, and increased government support, we are moving toward a world where nothing goes to waste, a future powered by sustainable energy and smarter resource management. And that's how 160 million batteries are recycled each year, turning old, worn-out power sources into brand new materials that drive the future of technology. Which part of this process surprised you the most? Let us know in the comments below. And if you enjoyed this behind-the-scenes look, make sure to like, subscribe, and stay tuned for more fascinating factory processes.